In this video, we'll prove 3 more tests about series. The ratio test states that given a series an with all the terms an not equal to 0, then if the sequence an satisfies that the limit of the absolute value of the ratio an plus 1 over an is equal to some real number r that's less than 1, then the series converges absolutely. An intuitive reason why this might be true is that a geometric series is one in which the ratio between subsequent terms is always some specific constant value r, and we demonstrated that those series converge precisely when the absolute value of r is less than 1. So you could think of this as an extension of that fact to allow us to deal with series that don't necessarily have a constant ratio between terms, but we can look at what that ratio approaches. We'll be able to prove this statement by comparing to a geometric series. Let's start the proof by assuming that the limit of the absolute value of an plus 1 over an is equal to some real number r strictly less than 1. Thinking of this as a sequence, it converges to r. And the reason we needed all the an to be non-zero is because of this divided by an. Since the inequality is strict, there exists a real number s that's strictly greater than r and strictly less than 1. Using the positive difference s minus r as our epsilon, it follows from the definition of convergence that there exists a big N such that n greater than or equal to big N implies that the absolute value of a term of our sequence minus r is less than our choice of epsilon, s minus r, and that absolute value of an plus 1 over an just represents a term of the sequence. And we can just delete the absolute values on the left-hand side and the inequality still holds because we've just made the left-hand side smaller. And then we can add r to both sides and multiply both sides by the absolute value of an, which leaves us with the absolute value of an plus 1 being less than the absolute value of an times s. And again, that's true for all n greater than or equal to big N. So let's write down the specific version of that statement for the index big N and for the index big N plus 1. The absolute value of a sub big N plus 1 is less than the absolute value of a sub big N times s. And then if we use the index big N plus 1, we could write that the absolute value of a sub big N plus 2 is less than the absolute value of a sub big N plus 1 times s. And combining these two together, we could say that the absolute value of a sub big N plus 2 is less than the absolute value of a sub big N times s squared. And in general, we could say that the absolute value of a sub big N plus m is less than the absolute value of a sub big N times s to the m for any index m. We need to demonstrate absolute convergence, so let's consider the series of absolute values of an. Let's pull out all the terms that we don't have a handle on, so every term with an index less than big N, let's just write it outside of the sum. And then I could have the sum say start at an index of big N, but let's instead express it as the sum from m equals 0 to infinity, and then instead of writing a sub m, I'll write a sub big N plus m. So this expression is the same sum, but it's sorted in a more helpful way. The first n-1 terms have no bearing on the convergence or divergence because there's only finitely many of them, so we just need to focus on the convergence or divergence of this sum. And for any m, 0 is less than or equal to the absolute value of a sub big N plus m, which is less than the absolute value of a sub big N times s to the m. And we know the series m equals 0 to infinity of absolute value a sub big N times s to the m converges because it's a geometric series with the common ratio s being strictly less than 1 in absolute value. So our series converges by comparison. And since the series of absolute values of an converges, we can conclude that the series sum of an converges absolutely. Now we'll turn our attention to Abel's test and Dirichlet's test. And to prove both of these, we'll need an algebraic identity called summation by parts, a discrete analog of integration by parts. Abel's test states that if the series sum k equals 1 to infinity of a sub k converges, and if b sub k is a non-negative decreasing sequence, then the new series sum k equals 1 to infinity of ak bk converges. One thing you might try for the proof is to use some sort of comparison test. See if you can spot what's wrong with this argument. Since b1 is greater than or equal to bk for all k, ak b1 is greater than or equal to ak bk for all k. And since the series ak converges, the series b1 ak converges by the algebraic limit theorem for series, and so the series ak bk converges by comparison. The reason this fails is that we don't have the other half of our hypothesis for the comparison test, the non-negativity of the terms of our series. We know the bk are non-negative, but we have no guarantees about the ak. So we'll need a different approach. The sequence bk doesn't necessarily converge to 0, but because it's decreasing and it's bounded below by 0, by the monotone convergence theorem, it converges to something. And so the sequence formed by the difference between subsequent b terms, like the sequence bk minus bk plus 1, converges to 0. This suggests that we should introduce those differences into our partial sums of the series we're trying to show converges. Let's show how this can be done by turning our attention to the summation by parts formula and then returning it and applying it in this proof. Assume AK and BK are sequences of real numbers, and let S sub n denote A1 plus ... plus AN. Then the sum from k equals 1 to n of AK BK equals SN BN plus 1 plus sum k equals 1 to n SK times BK minus BK plus 1. And notice that the sums in this statement are all finite. This is just an exact discrete identity, so we don't need to have any discussion of convergence. We just need to show that the two sides are equal to one another. The left-hand side exactly represents the nth partial sum of the series we're trying to show converges back in Abel's test, and the right-hand side involves those differences bk minus bk plus 1, which tend towards 0. So once we prove it, it'll be a useful substitution. What's most intimidating about statements like this is the notation. So if you were trying to prove something like this, what I'd highly recommend is to choose a specific value for n and literally write out all of the terms on both sides. You should see a bunch of cancellations occur, and then you'll end up with the same thing. And by actually doing the work of writing out all of these terms for various values of n, you'll be able to identify a pattern and write down a general argument. I want my proof of this to somewhat suggest how you might have come up with a formula like this, instead of just verifying that it's true. So I'm just going to start with that left-hand side, with those partial sums of the series we need to show converges, and then expand them in terms of the differences of the bk. I can split up that summation into its n terms, a1b1, a2b2, a3b3, up through an/bn. To express b1 in terms of those differences, I'll replace it with b1 minus b2 plus b2 minus b3 plus b3 minus b4, etc., all the way up through bn minus bn plus 1, and then I'll have to add on bn plus 1 again at the end so that this finite statement is still true, and I can distribute the a1 to each of those terms. Now let's replace b2 similarly with b2 minus b3 plus b3 minus b4 plus ... plus bn minus bn plus 1 plus bn plus 1, and then distribute a2 to each of those terms. And then we could expand b3 similarly, and distribute a3 to each of those terms. And we can do this for each term ak bk all the way up through an bn, which will just be expressed as an times bn minus bn plus 1 plus an times bn plus 1. And I'm writing the terms offset like this in a grid to align those differences bk minus bk plus 1. This makes it more clear how I could factor each of those differences out of every term containing them in this total sum. Let's add down each column. On the left-hand side, we have exactly the nth partial sum of the AK-BK series as expected. And on the right-hand side, let's work right to left. So at the very rightmost column, we can factor bn plus 1 out of all of those terms, and then we have bn plus 1 times the sum a1 up through an, which is what we called Sn. So that is Sn times bn plus 1. And then just to the left of that, we have a1 through an, each times the difference bn minus bn plus 1. So we factor all those out and express them as Sn as well. But as we continue to move to the left and sum columns and factor out all the a terms, we don't have terms all the way up through an. Like in column 3 on the right-hand side, that difference b3 minus b4 is only factored out of 3 terms, leaving us with the sum a1 plus a2 plus a3, or S3. And in the first 2 columns, we can factor out an S2 and then an S1. So in the kth column, we've factored out an SK from the difference bk minus bk plus 1. And that's true for the first n columns. So those all combine to exactly the sum from k equals 1 to n of sk times bk minus bk plus 1. And that n plus first column on the right-hand side is exactly the extra term Sn times Bn plus 1. So we've proven the identity, but even if we didn't have the identity to start with, we would still be able to apply this technique to that partial sum we were interested in to express it in terms of these differences. And while this formula will be sufficient for the proofs of our 2 theorems, this isn't the most general summation by parts formula. As an exercise, see if you could prove this version of the summation by parts formula, where our index doesn't necessarily start at 1, but starts at any constant. Returning to our proof of Abel's test, since the series of the AK converge, the sequence of their partial sums, Sk, converges, and so it's bounded by, say, some real number m. Looking at the summation by parts formula, the sequence Sn Bn plus 1 converges by the algebraic limit theorem, because Bn plus 1 is just a scalar, and the sequence Sn we already know converges. And for the sequence whose terms come from that summation in the second term on the right-hand side, we want to apply a comparison test using the bound big M, but some of the terms might be negative. So let's argue that the series sum k equals 1 to infinity of sk times bk minus bk plus 1 converges absolutely. We'll look at the series of its absolute values and say that this, term by term, has to be between 0 and big M times bk minus bk plus 1. But this is a telescoping sum. Looking at, say, the nth partial sum of the series we're comparing to, we can factor out the big M and cancel all the terms in the middle, just leaving us with b1 minus bn plus 1. And looking at the limit of this expression, b1 is just a constant, and the sequence bn plus 1 is just a reindexed version of the sequence bn, which we know converges. We said that earlier from the monotone convergence theorem. So this sequence of partial sums for the series we compared to converges, and so by comparison, the sequence whose terms are k equals 1 to n sk times bk minus bk plus 1 converges. And so by the algebraic limit theorem, combining the convergence of the two parts of the right-hand side in our summation by parts formula gives us the convergence of the left-hand side, which gives us the series convergence for the sum k equals 1 to infinity of ak bk. Both this version of Abel's test and Dirichlet's test, which I'll state momentarily, could be made stronger by weakening certain hypotheses. When we prove a theorem, it's important to think about where each hypothesis was used, and if a weaker version would suffice, leading us to a more general result. In this proof, the boundedness of the partial sums sk was all we used to demonstrate the convergence of the second term on the right-hand side. The only time we really used the convergence of those partial sums was for that first term on the right-hand side. So Dirichlet's test will be a slight modification of this that doesn't require the convergence of those partial sums, but instead requires that that sequence bk converges to 0. So again, assume ak and bk are sequences of real numbers, and let s sub n represent the sum a1 up through an. If the sequence Sn is bounded, but not necessarily convergent, and the sequence Bk is non-negative, weakly decreasing, and converging to 0, then we get the same conclusion, that the series AK-Bk converges. The proof of this test would be basically identical to the proof of Abel's test, with the one modification of how we'll deal with the Sn Bn plus 1 term. Instead of saying that it converges because the sequence Sn converges, we'll now instead say it converges because the sequence Sn is bounded by, say, some real number m, and then the sequence Bn plus 1 converges to 0. And then to fully justify this conclusion, you could go back to the definition of convergence, but you don't need to because we've proved several basic facts about sequence convergence. So for instance, let's use the algebraic limit theorem and the squeeze theorem. We can note that the sequence m Bn plus 1 and negative m Bn plus 1 both converge to 0, and our sequence Sn Bn plus 1 is bounded between them. So by the squeeze theorem, it converges to 0 as well. We'll have one more video on series of real numbers where we turn our attention to infinite double summations, one of the objects we considered back in episode 5 as an example of why we even need rigor in the first place.